my background is in architectural engineering and civil engineering, not in computer science, but we do borrow from computer science and data science and use in our methods. I'll take you through different projects, in a way, a journey through of which my group has taken to describe to you what I mean by people-centric AI for the built environment. So I'll start with defining cognitive built environments. So as an architect and a civil engineer, obviously I'm concerned with buildings and infrastructure. And what I mean by cognitive built environments are the environments that can perceive, sense, reason what's happening, and collaborate with their users. And this is the most important maybe message that I will try to give to you for supporting decision-making, problem-solving, safety, security, learning, productivity. And these goals will change depending on the type of the building and function and purpose of the building. So I have 3 images just to show you, and these are from popular topics that we have been discussing. Autonomous vehicles, socially assisted robots, space operations. So in my world, the buildings are the machines. So I'm just trying to put the framing here. So when you think about cognitive built environments, or when I say human-machine collaboration, you should be thinking about buildings or built environment and the occupants and users of the built environment. So there are some important definitions. So in my definition, these cognitive built environments, they learn, predict, and adapt and change user behavior as well as building behavior. They interact with their users in a natural way, and natural is in parentheses because we try to make this happen as much as possible. And we reason, these buildings or cognitive built environments reason with a purpose. So it could be user satisfaction, the purpose, comfort, productivity, and such. Even though majority of the work I will show you are going to be around residential buildings or office buildings, I have this slide here because recently we have started to expand our focus to different kind of built environments, focusing on cognitive construction sites or cognitive public buildings like metro stations or airports, as well as other types of buildings focusing on health and well-being, for example, in hospitals. So I'll also introduce my research group. I have several PhD students, master's students, and undergrads working with me. And the lab is called Innovation in Integrated Informatics Lab. And we focus on acquisition, modeling, and analysis of the data needed for these cognitive built environments. And we also design algorithms and visualization techniques, again, to improve built environment efficiency, maintainability, sustainability, and such. So we use various methods, including sensing, modeling, and modeling, both mathematical modeling as well as geometric modeling, prediction, and we also have control and actuation in buildings as well. So it's important to mention that the work that I will show you is not just my group's work. We do collaborate quite a bit interdisciplinarily. I have colleagues working with me from education, learning, architecture, computer science, communications, and recently I started collaborating with an occupational scientist as well. So the topic is quite multidisciplinary, as you can imagine. Therefore, the projects have to have that multidisciplinary nature. So I organize different projects my group has conducted throughout the years. Some of them are older, and they're there to show you the progression of research and our thinking in the group. And also the categorization is related to how different steps that must be taken for us to get into people-centric AI for the built environment. So just to, I don't know if this framing or convincing is needed. But just to show you how built environments are alive, we have started with this Department of Energy project maybe 9 years ago, where we were really interested in understanding what's happening in the building in terms of its occupancy as well as comfort of occupants. So we have developed these sensor boxes. We're talking about, again, 8 years ago, where we weren't sure what sensors to use, but these are the sensors that we placed in those sensor boxes and place them in every room of a testbed building in our campus. I do not have any of the details in terms of algorithms or the methods, so I hope I don't disappoint anybody, but I'm happy to talk to you after the talk. So what we have done here is one of the difficulties that we were challenged with is the ground truth collection in an office building. It's a very real problem because people didn't want us to put cameras. So the innovation here in this project, if I may describe it one sentence, was basically creating a couple models to be able to transfer what we have learned through those models into the entire building in terms of learning its occupancy. We have tracked people, occupancy throughout several months. And here, just a demonstration of occupancy, and the blue rectangles are basically different thermal zones. This building, if you're familiar with United States, is centrally controlled in terms of its heating, ventilation, and air conditioning. So this was the accumulated occupancy in April, May, and June. So I mean, these three slides are there to show the occupancy changes. This is an academic building, and I've seen occupancy actually changing drastically here as well. However, we were operating these HVAC systems of this building from 6 a.m. to 9 p.m. to its full occupancy. As you can imagine, there are quite a bit of energy inefficiencies. So we have taken the data and created occupancy presence graphs similar to these ones for different days, different weeks, as well as different seasons. And they look like this. This is one floor and 28 offices. As you can see, there are different occupants have different occupancy probabilities. And now we have basically put these occupancy profiles into Energy Plus and simulated energy consequences of basically running the building based on people's occupancies. I do not want to get into so much into how much savings there are, because I know, and you also probably know, that these savings change depending on the building type, the construction, when the building was constructed, as well as the climate. But this slide is here to show you that in Los Angeles, at least based on the occupancy of the building, we can save a substantial amount of cooling energy. So presence of occupants is fairly easy compared to some other things that concern occupants or people in buildings. So one of the questions is how to extract the condition of mind. And as part of this project, we were really interested in understanding people's thermal comfort preferences. This stemmed out from a very personal need. I live in Los Angeles. It's a fairly mild climate, Mediterranean climate. I have a blanket in my office in the summers because we overcool our buildings quite a bit. So I wanted to understand what is the thermal preferences of people and how can we extract this information from people. Again, this is an older project. We started with participatory sensing and developed this app. There are some differences between what you see right now that are available, applications available in the market than this one. One of it is we basically left the slider quite personalizable, right? I prefer this, I prefer that. Intentionally, instead of saying I prefer 23, I prefer 25 Celsius degrees, because we've run some experiments and realized people really don't know what they prefer. And then also that scale changes as well. So we used a fuzzy rule-based descriptive and predictive model to be able to basically understand the range that people are comfortable, and this is very personalized again. So taking these ranges, we do not feel, we're not comfortable within or in a degree, it's a range, right? And this range changes for different people, depending on your gender as well as your background, and cultural background really affects this. Americans have a very narrow thermal comfort range compared to Middle Easterns or Asians, for example. And one thing that I have to say is a larger thermal comfort band is a good thing for your health and for your metabolism. Anyway, so we have developed our own controller in that building, and we have run some experiments following the facilities management practices as well as people's preferences. Again, here you can see when we compared our controller, as you can see how old this research is, 2012 we're talking about, to the facility management, we were able to save 40% or so in terms of airflow. Again, the numbers are not as important here. Then we got interested in, okay, if it's a range, can we change a set point that's going to make people comfortable, but also is the most energy efficient, depending on the outside temperature, right? So we looked at the energy and comfort trade-off, and within that range, we picked intelligently the set points and operated the building, and we were able to gain further savings. From there, we really got interested in, can we predict comfort? Instead of asking people what they prefer, because this is not very sustainable, even the most enthusiastic people stop basically using apps. How can we basically extract this information without asking people? So that took us to another journey from participatory sensing to looking into sorry, what's the term? Anyway, okay. Vasodilation, which is increasing of blood flow, and vasoconstriction, which is limiting of blood flow. The name is going to come to me. And we developed basically this very nice looking glasses with infrared sensors on them. So nobody would wear this, obviously. But we were trying to prove a point of proof of concept. Then we have developed much nicer devices like this one. And what we have done here is basically we looked at the cardiovascular territories on face, and we looked at measurements in 5 different points on face, and developed 2 heuristics with 95% probability of females and males separately, because as you can see, the measurements on a female face is much lower on different points than a male. Therefore, females feel cooler in the same temperatures usually than the males. So we developed 2 heuristics for females and males to feel cold or hot, and the probability of this happening. So we have taken this, and this research is continuing. Now we're looking into thermal cameras and how we can use thermal cameras so that people don't wear something which is uncomfortable, right? And uninvasively basically predict people's thermal comfort. But there are some nuances, right? Depending on the building design, and depending on the mechanical systems design, as well as who your neighbor is and what he or she prefers, if he or she is there. This is not a very straightforward concept in terms of focusing on comfort as well as energy efficiency. So how do we learn what are the most optimal set points given this complexity in building? So this is another project where we introduced a model-free control policy, and it began learning optimal set points with no prior historical data and optimize HVAC operations. So each day more and more data came in, and these were things like gas and electricity consumption, weather and occupancy, and it was able to find optimal set points for the next day. So again, we ran simulations and we were able to save 31% of energy savings. So one of the questions I recently asked to one of my students is, okay, what if we make enough progress and we, in a non-contact, non-intrusive way, sense people's comfort and try to operate buildings per people's comfort? So how much, what kind of an outcome we will be able to achieve? We don't have as many comfort profiles in our research group or other research groups. So we have developed synthetic comfort profiles using ASHRAE's RP884 database. Basically for 4 climates, we developed 400 profiles. And we ran energy simulations. And I like this slide because it goes back to the point that I was trying to make at the very beginning of my presentation. It really depends on how much you can save, depending on the type of the building, when the building was built, type of construction, as well as the climate. But what we were interested in is, I don't know if you're familiar with thermal comfort research, but buildings are supposed to provide comfort to 80% of their occupants. So this is the ASHRAE's requirement. We looked at comfort. Here you can see that the blue one is the DOE recommended set point with cooling and heating set points. This green one is the fixed building set point, which is 23 Celsius degrees. And this is when we ran the building based on the synthetic comfort profiles that we have generated. In none of the cases we are able to make people happy, 80% at least. I mean, we're far away from that. And we looked into what is happening, and what's happening is as long as you have more than 3 occupants in one thermal zone, we basically cancel out each other. So the systems that we're designing, at least in the States, are not very efficient in terms of making people, satisfying people. So this research got us into the investigation, like how do we make multiple occupants of buildings satisfy, right? And this is a very real project. And here, this is a collaboration with a global engineering firm, Arup, and they have developed this IoT desk with multiple sensors on them. And you can basically laser cut different pieces and put it together. As you can see, my colleagues from Arup are building the desk. And it has different features in terms of ID recognition, and as well as I mentioned, different sensors that would learn your preferences. So what we're trying to do in this research, taking that IoT desk and creating an intelligent, basically workstation that is going to learn your visual comes in new, I haven't talked about it yet, and thermal comfort preferences, as well as your sit-stand regimen and your posture, and taking your baseline and trying to take you towards a more ideal baseline in terms of your health. As I mentioned, the wider thermal comfort range is better for you, and different light, color, and intensities are good for you depending on the tasks that you're doing, as well as standing up all day is not as healthy as sitting all day. So the whole idea here is this desk basically negotiating with you, and the desk's motor functions work with the user's motor functions to basically take the user's mind towards the ideal conditions. So that's the project that we are working on right now, and hopefully, and it is about to be funded by the National Science Foundation as well. So tasks or activities differ in a building. Like one size does not fit all for all occupants. One size does not fit for all activities either. So this is another student and another research project where we have developed algorithms to recognize activities in real time. So basically, before you're about to do an activity like cooking or grooming or watching TV, knowing what activity is going to take place in the space and automating your appliances based on that intelligence. So we have run several tests in 2 apartments and an office. This slide is quite busy, but it's there basically to show how different people's profiles are for doing same activities, right? The appliances you're using, your energy profile, how much you're using different appliances, and how much you're using your time on different activities are different. So this is another graph showing the same information in a different way. These were similar size apartments. Here you can see, and there are only one occupant in each of these apartments. One of the persons is consuming 3 times more energy than the other person. We have also looked at the office and looked at how people are wasting and the waste profiles. And here you can see standby power is the blue, and unneeded appliances being left on is another energy consuming area. So as you can see, our energy profiles are different, so are our waste profiles. We also looked into the activities and how we're using, what kind of appliances we're using, for example, for cooking. And there's a lot of insight, obviously, we know this from others' research as well. But this is, at this point in the presentation, I start getting some very concerned looks. Because we're basically getting into privacy concerns and understanding, I mean, smart could be good smart or bad smart, right? And also, automation preferences differ as well. So we have run several surveys and looked into people's preferences, and this also very much depends on the person. For example, one profession, computer scientists, did not want us to touch their computers. I mean, depends on what you're doing and what your profession is and such. And then you prefer different levels of automation depending on the activities as well. So this whole exercise was basically understanding people's automation preferences and how these preferences change in time as well as different situations. We also looked into, I'm going to fast forward these slides because I'm quite behind with the presentation, looked at people's personalities, how being agreeable or being high on neuroticism or openness changes basically your preferences. We developed a model to predict people's preferences, and this is an ongoing research that I'm happy to discuss with you. We're going with this. So we know what's happening in the environment. One area that I want to continue discussing, and I'll go through these slides quickly, is understanding why this is happening. So I call this human building interaction compared to a more standard concept of human-computer interaction, in which a user interacts with a machine through a well-defined medium, like a screen. In human building interaction, we're immersed within the building, and our interactions are quite complex and coupled, and they're influenced by many factors. At the same time, these interactions result in satisfaction or dissatisfaction directly because of the nature of buildings. Also, as I mentioned, there are multiple buildings and an environment in the neighborhood, as well as multiple occupants. And through this line of research, we're trying to understand why people are making the decisions they're making. And there are multiple reasons, like the building properties, the physical environment, temporal conditions, as well as physiological, psychological, and social reasons, right? And all of these come together and trigger a reason for you to interact with your building. At the same time, we really got interested at this point on understanding impact of design on these decisions. And I'll show you a couple projects how we're trying to investigate because that's another variable that needs to be taken into account. So very quickly, so these are some series of experiments with our social scientists. And in this slide, what I'm showing you is the same office. In one of the in one of the groups, we basically told people that this is an energy efficient building. It's LEED certified, and the same space. We just said this is an office building without any branding, and we ask people to set the lighting in terms of use of natural light or artificial light, and we ask them to recycle a piece of paper. So what happened is basically when people thought the building is energy efficient, they behaved better. Nothing was different, so this is a completely psychological effect. In another experiment, we looked into control and providing remote control to people and how that changes people's behavior. And again, going a little bit fast, basically when people had remote control, they used that device. If they had remote control for the blinds, they opened the blinds. If they had remote control for the artificial lights, they turned on the artificial lights. In another experiment, we looked at how setting the office prior to an occupant entering the office changes people's behaviors. And in this experiment, we had 5 different default settings. And what we have realized is the stickiness effect. Basically, people are more likely to have a final choice that resembles the default. And then there are all kinds of other details, but interactions also significantly reduced when daylighting was part of the default. We also looked into people's lighting preferences. I'm going to fast forward for the interest of time. And we have collected all this information to basically understand impact of us on energy consumption versus out-of-the-box assumptions, for example, an energy simulator like Energy Plus does. And you can see different, how different basically energy consumption is depending on people's behavior. Right now we're looking into multi-sensory stimuli. So what happens basically when you have multiple discomfort factors, you have glare and heat gain in the space. What happens if you have multiple occupants in the space? And how do we react to these? And we're basically looking into different interaction patterns. And this is an experiment, preliminary results, the same office facing south versus north, and how people basically interact and how these patterns change in this 2 different orientations, the same office. What we want to do is basically understanding the impact on design. So that's one example of basically ability to take all of this information and creating kinetic partitions or kinetic facades. Not only taking into account what's happening outside in terms of weather conditions, but also taking into account people's preferences in the building as well. All right, so the next step is I'm talking to our neuroscientist colleagues to understand if we can use their expertise to be able to extract some of this information. Okay, fast forward. So in some cases, buildings can make people happy by providing the conditions that they would like. In other cases, the buildings have to communicate with the users because there's an unoptimal condition or a condition that a building cannot provide. So in this line of research, we looked at today's conversation. And this is what it looks like, right? Either the building listens to its occupants, basically you're setting up your smart thermostat and such, or the building speaks to its occupants and says, oh, you're doing great, look, I'm turning this device into green and such. But we wanted to go from this monologue to a dialogue and try to create a communication between the buildings and its occupants. However, we don't want the communication to look like this, and there are increasing concerns about how our lives might turn out with these very intelligent devices that we have. And in this research, I collaborated with social scientists and computer scientists that focus on virtual humans. We wanted to create this interaction between a building and its occupants through agents that have relational features. So very similar to this robot having a face and a body, as well as Alexa having a female voice. We wanted to build this relationship through Ellie. So this is Ellie. So let me turn up the volume.
If I open the blinds for you to have natural light, would you please dim or turn off the artificial lights?
So basically, we had a male version and a female version representing a building or a facility manager and asking hundreds of people to do something for her or him. And we have repeated this experiments multiple times as well. So hold on. So, okay. No surprise here. Avatars were more effective than voice than text-based communication. And participants complied more with the request coming from a female agent. This is also no surprise. You have your navigation systems with female voices and such. One thing we wanted to test here is, does this carry to a building, right? So that was the part that we weren't sure. And people were really not as compliant when they thought the building talking to them versus the facility manager is talking to them and asking something. And I mean, this might change as we interact more with devices and inanimate objects, but at the time we conducted this research, this was the conclusion. Then we took Ellie and we created a more social Ellie through social dialogue.
Hi, how are you? I'm Ellie, representing your building. What's your name? I'm glad to see you here. If I open the blinds for you to have natural light, would you please dim or turn off the artificial lights?
So it's the same Ellie basically talking to you a little bit more, knowing you, your name, how you're doing, all that kind of stuff is a simple intervention. And in this condition, there were significant effects of building persona. So when people started having a social dialogue with an avatar that they thought is a building, they complied automatically more. So that really gets into how we build our social ties with things. And then females were more compliant when engaging in a social dialogue as well. So from here, I mean, this is a long line of research. We want to mathematically basically predict what kind of a persona should approach you at what time. I mean, there's so many nuances, right? And predict your response and approach to you based on that prediction is where we're trying to go. So can a building speak to its users in other ways? So this is another research project. Instead of having a face and a smile and looking like a person, in this line of research, we're trying to visualize information through augmented reality and virtual reality. So with the advancements in our world right now, soon we will be able to have different layers of information integrated into our reality. So what if the buildings were able to show you, in this case, light maps showing light intensity, right? What if in the next frame you're going to see the building basically trying to communicate to you the heat gain through the windows and how that heat gain basically causes HVAC systems or the lighting systems to consume energy. So would you be changing your behavior with this added information? So we're running experiments. I don't have results, so I'm happy to share them with you once I have them. So most of these research projects were related to energy. As I mentioned at the very beginning of my presentation, we're also expanding our scope to different areas. So this is the project very briefly I'll talk about because you might be potential participants. We're looking into how and if building design has an impact on people's emergency behaviors during building emergencies. So if we know this information, can your building influence your behavior during these unfortunate events, right? What is the relationship of adjacent adjacent spaces, the flow, different building attributes, and such on people's evacuation behavior? So we're trying to extract this information. The continuation of this project is likely to be looking at active shooter incidents and how people are behaving in those extreme of violence type of events, and how a building could help its occupants in case of these kind of again, unfortunate events, I guess. So I have my student here. He has some flyers if you would like to learn a little bit more and also participate in our experiments, as Darren said. We're going to be running physical experiments. Another research that we will be looking into is human-robot collaboration with a very specific focus on construction sites. So I didn't mention, but I also have a background in construction engineering and management. So this is what our worlds look like. It's very different than the manufacturing factories, right? We have rain, we have dust, we have dangerous conditions, uneven surfaces, and we are increasingly using construction robots. So this one is SAM, semi-autonomous masonry, and it can lay bricks 3 or 4 times faster than a construction worker can. But the devil is in the details, right? This robot has to work on a scaffolding, and it is semi-autonomous. There needs to be a worker feeding the brick to the robot. There's somebody watching the work and measuring the quality and taking out the excessive mortar and such. So construction sites are far away from being completely autonomous is the message here. So how do we build trust between robots and workers? And workers were talking about sometimes different proficiency levels in terms of language or skills. Or education, right? So what we're trying to understand is what can be done to build trust between a construction worker and a construction robot. And then we're looking into the implications of this on construction work processes, because this is likely to change work packages, number of crews, where the crews are going to be located, and all that kind of stuff. This is another project. I'm collaborating with a group in the USC campus, and the group is focusing on learning of students with different learning disabilities. And in this project, we're renovating the entire floor for this center and building the space in a way that's going to accommodate different learning needs of different populations. And another initiative that we're taking on is this new center. We're going to be looking into the intersection between intelligent environments, technology, and society. Specifically, we will be looking into interaction and trust and heterogeneous teamwork environments, and how all of what I've been talking might be changing design, construction, operation, and use of intelligent built environments. Of course, privacy and security are of our concerns as well. So these are some of the research questions. I'm not going to read them to you, but how will AI change people's expectations from and perceptions of built environments, right? Can the built environment augment its users' performance. I've talked very briefly about learning in a classroom setting, for example. What are the effects of human building collaboration on productivity, taking into account the IoT desk and an office environment that I have been talking about? How can we better design buildings to provide novel interaction opportunities? And how will these interactions change human and building behavior? So these are some of the questions that we will be continuing exploring. So I think I'm almost there. So with that, I will skip this one and thank all of my former and current students. And I'll just leave you with a small clip from a podcast, hopefully it's going to play. And I think that small clip captures what I have been trying to communicate here.
What if your home was more than that? It was more than just an address. What if your home was like your friend?
What are you thinking?
You know, you and I enter our office building, your space would be personalized to you. Your space would know you in a very intimate way. Your space would know if you had a bad day or a good day, if you were tired and you needed more coffee, if you had appointments that day. Your space would be like your friend. It would be an extension of you.
That sounds interesting.
What if it could have a personality?
All right.